Hi guys, welcome back. Next topic is our convection, question based on convection. First question is laminar forced convection over a flat plate. Free stream velocity is increased by a factor of 2. We have to find average heat transfer coefficient. We know that Nusselt number relation for laminar flow is 0.664 for flat plate, 0.664 Reynolds number to the power 1 by 2 and Prandtl number to the power 1 by 3. And Nusselt number we know is equal to HL by K, and Reynolds number is velocity into dimension, diameter dimension upon viscosity. So from here, from this relation, we see that our heat transfer coefficient is equal to velocity to the power half under root of velocity. So h1 by h2 would be equal to v1 by v2 to the power half. So this is our average heat transfer coefficient can be calculated from this relation. Next question is water flows through tube diameter 25 mm at an average velocity of 1.0 meter per second. Water property is given as density 1000 kg per meter cube, mu viscosity is given as 7.25 into 10 to the power 4 Newton second per meter square, K 0.625 watt per meter Kelvin. Prandtl number is given as 4.85. So and the Dieter-Boiter relation is given in the question only. Nusselt number is equal to 0.023 Reynolds to the power 0.5 Prandtl to the power 0.4. And we have to find our heat transfer coefficient H in watt per meter Kelvin. Reynolds number we know is rho v d by mu. So we know the values of rho, density, v and d and mu. So putting in the values, our Reynolds number come out to be 34,482.75, which is more than 4,000, and it is a turbulent flow. And from here we can say that Nusselt number is equal to HL by K, which is equal to the given Dieter-Boiter relation. So putting in the values of L and K and Reynolds number and Prandtl number given in question, we can find our H equal to 4613.6 watt per meter square Kelvin. Next is viscous laminar flow of air over flat plate. Boundary layer thickness rho for plate length L is given, and if the plate length is increased thrice its original length, we have to find the percentage change in laminar boundary layer thickness. So boundary layer thickness we know is directly proportional to root x. So for boundary layer thickness of 1 is 2, boundary layer thickness of 2 is equal to root of x1 by x2. So x1 is our length 1 and x2 is basically thrice of length 1, which is equal to 3x1. So it would be x1 by 3x1. So boundary layer thickness of second surface comes out to be 1.732 of first surface. So we have to find the average change. So thickness of second surface minus first surface upon first surface into 100 would give us the percentage change in the thickness, which comes out to be 73.2%. Next question is fluid of Prandtl number is given as 1 at 500 Kelvin, flows over flat plate of 1 meter length, maintained at 250 Kelvin. Velocity of fluid is 10 meter per second. Kinematic viscosity is given as 30 into 10 to the power minus 6 meter square per second. We have to find thermal boundary layer thickness rho t at 0.5 meter from the leading edge. Prandtl number to the power 1 by 3 we know is equal to rho by rho t. Rho is our thermodynamic boundary layer thickness and rho t is thermal boundary layer thickness. And if Prandtl number is 1, then thermal boundary layer thickness rho t would be equal to thermodynamic boundary layer thickness rho. So Reynolds number is equal to velocity into length by viscosity, kinematic viscosity. So velocity is given as 10, length we have to find at 0.5 meter from leading edge upon viscosity 30 into 10 to the power minus 6 given in the question. Reynolds number comes out to be 1.6 into 10 to the power 5, and for flat plate it is laminar flow. Then rho, which is hydrodynamic boundary layer thickness equal to thermal boundary layer thickness. It would be equal to, this is a given formula, 4.94x by under root of Reynolds number into x. 4.94 into x is our length, 0.5 upon under root of Reynolds number, which we have calculated, into length 0.5. So our thermal boundary layer thickness rho t comes out to be 6.175 mm. Next question is, Prandtl number is given to us 0.050. Friction coefficient CFX is 0.50. We have to find Stanton number. From Reynolds-Colburn analogy, we know that for friction coefficient it is given that CFX, friction coefficient, by 2 is equal to Stanton number into Prandtl number to the power 2 by 3. So from this relation we can calculate our Stanton number, which is equal to CFX 0.50 by 2 into 1 by Prandtl number to the power 2 by 3, and their Stanton numbers comes out to be 1.83. Next is, hydrodynamic boundary layer thickness of fluid over a plate is 1.2 mm, and we have to find the thermal boundary layer thickness. Rho is given to us. We have to find rho t. Mu is 8.5 into 10 to the power 4 Pascal second. Cp, specific heat, is 4.3 kilojoule per kg Kelvin, and K is given as 0.6 watt per meter Kelvin. So Prandtl number we know is rho Cp by K, and also we know that Prandtl number to the power 1 by 3 is equal to rho by rho t. Sorry, del by del t, where del is hydrodynamic boundary layer thickness and del t is thermal boundary layer thickness. So equating from this relation of Prandtl number, we find that mu Cp by K to the power 1 by 3 is equal to rho by rho t. So putting in the values of mu, 8.5 into 10 to the power minus 4, and Cp, specific heat, 4.3 into 10 to the power 3, by K, conductivity, given in question, 0.6 to the power 1 by 3, is equal to rho, hydrodynamic boundary layer thickness, given as 1.2, and thermal boundary layer thickness, which we have to calculate. So putting in the values and solving it for rho t, we find our rho t is equal to 0.65 mm. Next is turbulent natural convection. Till now all those questions were for forced convection, and here natural convection is clearly mentioned to us. So for turbulent natural convection from vertical wall at 240 degrees Celsius with still air at 40 degrees Celsius, Nusselt number is given as 28. If wall temperature becomes 60 degrees Celsius, temperature is increased. So now we have to find the new Nusselt number. So Nusselt number we know is equal to C into Kirchhoff number into Prandtl number to the power 1 by 3. So from here we can say that Nusselt number is equal to T to the power 1 by 2. So Nusselt number for first situation is 2 for second situation is equal to temperature difference for 1 upon temperature difference for the second situation to the power 1 by 3. So NU1 we know 48, NU2 we have to find delta T1. Initially it was 240 degrees Celsius and with still air at 40. So 240 minus 40 upon, now the temperature has become 60 degrees Celsius. Sorry, this is 60 minus 40 because now the new temperature is 60 and still air is at 40 degrees Celsius. So from here we can calculate our Nusselt number for the second situation. Next question is air temperature T infinity is given as 50 degrees Celsius, flows over flat plate with free stream velocity V infinity. Plate temperature is given as 200 degrees Celsius and temperature T at any given location is given by this relation, and where Y is distance measured around its normal of the plate, rho T thermal boundary layer thickness, rho thermodynamic boundary layer thickness, rho by OT we know is equal to Prandtl to the power 1 by 3, and rho is given as 0.55, mu of air is 2.5 into 10 to the power minus 5, K is given as 0.04, Cp of air is 1 kilojoule per kg Kelvin. So we have to find heat transfer coefficient Hx. So for Hx we know that is minus Kf del T by del Y at Y is equal to 0 upon Tw minus T infinity, Tw being temperature of plate and T infinity is surrounding temperature. This equation comes from the energy balance on thermal boundary layer. So this is an important equation which we can use directly to find our Hx. So to find Hx, first we find our del T by del Y, the relation given in the question. If we would differentiate it with respect to y, for y is equal to 0, we would get del T by del Y is equal to minus 2 T infinity minus Tw upon rho T, and so Hx would be equal to, putting in this in Hx in the given equation, if we would put del T by del Y which we have calculated in here, so our Tw minus T infinity would cancel out each other and Hx would come out to be 2 into Kf by rho T. Kf is thermal conductivity of fluid. So we know that rho by rho T is Prandtl to the power 1 by 3 and Prandtl number is equal to rho Cp by K. So rho T would be equal to Prandtl number to the power 1 by 3 by rho, and Prandtl number we have calculated putting in the value of mu Cp by K. So putting the value of Prandtl number here, we can calculate our rho T which comes out to be 0.584 mm, and in this equation of Hx to Kf by rho T we would put the values and our rho T comes out to be 136.80 watt per meter square Kelvin. Next we have is main air conditioning duct of rectangular shape, 400 meter is to 800 meter, has air at atmospheric pressure and 120 degrees Celsius, flowing with a velocity of 7 meter per second, and our viscosity is given as 15.06 into 10 to the power minus 6 meter square per second, and conductivity is alpha is given as 7.71 into 10 to the power minus 2 meter square per hour. So heat leakage we have to find out in watt per length per unit delta T. We have to find Q upon meter square per Kelvin, per length per unit temperature. So Reynolds number we know is velocity V infinity D by our viscosity. So in case of rectangular, if the shape is rectangular, our characteristic diameter would be 4 into area upon perimeter. So RE would be V is given as 7 into 4 into area would be L into B upon perimeter 2 into L plus B, and viscosity is given as 15.06 into 10 to the power minus 6. So Reynolds number come out to be 24.8 into 10 to the power 4. It is turbulent more than 4000 for the this is basically a even though the shape is rectangular, but it is a case of pipe, rectangular pipe. So for that it is turbulent flow more than 4000. So for turbulent pipe, we know that Nusselt number is equal to 0.23, Reynolds number to the power 0.8, and Prandtl to the power 0.4. And we know that Prandtl number is equal to mu Cp by K is equal to viscosity by alpha conductivity. Sorry guys, alpha is our diffusivity and K is conductivity, and alpha is equal to K by rho Cp. So for Prandtl number, we know that Prandtl number is equal to mu Cp by K, and it is equal to viscosity by diffusivity. So putting in the value of viscosity, which is 15.06 into 10 to the power minus 6, and diffusivity 7.71 into 10 to the power minus 2, and it is given, its unit is given as meter square per hour. To convert it into second, we divided by 3600. So Prandtl number comes out to be 0.703. Now putting the values of Reynolds number and Prandtl number in our equation of Nusselt number, Nu is equal to 0.23 into Reynolds number to the power 0.8 into Prandtl number to the power 0.4, we get Nusselt number as 413.12. So we know Nusselt number is equal to H into D by K, and from here we can calculate our H is equal to Nu into K by D, and H comes out to be 2.07. And we know that our heat transfer Q is equal to HA delta T, and in this case area is perimeter into length into delta T. So according to question, we are asked to calculate heat leakage in watt per length per unit delta T. So what we are going to do is, we are going to take our length and delta T to the other side, that is Q by L delta T, which is asked to us in question. So it would be equal to H into perimeter. So H we have calculated, perimeter we know twice of L into B, so Q upon heat transfer, heat leakage in watt per length per unit temperature comes out to be 448.17. Next question is, laminar convection rectangular plate at 170 degrees Celsius is taking place. Still air is at 10 degrees Celsius. Nusselt number is given as 50. If plate temperature becomes 90 degrees Celsius and length is cut down to half, we have to find our average Nusselt number, the new Nusselt number. So Nusselt number we know is equal to C into Kirchhoff number into Prandtl number to the power 1 by 4. Because it is laminar flow, so the power becomes 1 by 4. And Kirchhoff number we know is equal to delta T into length cube. So for the second Nusselt number which we have to calculate, Nu2 upon Nu1 would be equal to C Kirchhoff number 2 to the power 1 by 4 into Prandtl to the power 1 by 4 upon C into Kirchhoff number for first relation to the power 1 by 4 into Prandtl to the power 1 by 4. From this relation, Kirchhoff is equal to delta T L to the power Q. Kirchhoff is directly proportional to delta T and L to the power 3. We are going to put it into this equation. So Nusselt number would be equal, directly proportional to delta T into L cube to the power 1 by 4. From both these relations, we can see that Nusselt number is directly proportional to delta T L cube to the power 1 by 4. So the initial length was L, and now the final length has become half of it. So it is L by 2. So, and delta T1, so initial temperature difference was 170 with still air at 10 degrees Celsius. This was 160 degrees Celsius. Now the temperature has become 90 degrees Celsius and still air is at 10 degrees. So delta T2 temperature change has become 80 degrees Celsius. So putting in the values of delta T2 by delta T1 and length, new length which has become half L by 2 cube upon L cube whole to the power 1 by 4, we get our Nu2 is equal to half of Nu1. So our new Nusselt number is half of previous Nusselt number, which comes out to be 25. Next question is metal plate of 0.609 meter high form vertical wall at an oven and is at temperature 161 degrees Celsius, which is equal to 434 Kelvin. Within oven air temperature is 93 degrees Celsius, that is 366 Kelvin. Natural convection is taking place. Air properties at 400 Kelvin is given as viscosity is 26.4 into 10 to the power minus 6 meter square per second. Our diffusivity is 38.3 into 10 to the power minus 6 meter square per second. And conductivity is given as 33.8 into 10 to the power minus 3 watt per meter Kelvin. We have to find Rayleigh number. So we know that Nusselt number is equal to C into Rayleigh number, and Rayleigh number is equal to Grashof number into Prandtl number. And Grashof number is G beta delta T L cube by viscosity square. So beta is basically 1 by temperature mean. So 1 by the temperature given to us are 434 Kelvin and 366 Kelvin. So beta is 1 by temperature mean. It comes out to be 2.5 into 10 to the power minus 3. And we would put the values in Grashof number equation. So G is 9.8 gravity, and beta we have calculated 2.5 into 10 to the power minus 3 into temperature difference, that is 434 minus 366, into length given as 0.609 Q upon viscosity square given as 26.4 into 10 to the power minus 6, and Prandtl number, which is mu Cp by K, is equal to viscosity by alpha is equal to 26.4 into 10 to the power minus 6, viscosity given in question, and alpha being the diffusivity also given in the question, 38.3 into 10 to the power minus 6. So from here we get our Grashof number, and then we calculate our Prandtl number, put it in Rayleigh number, which is Rayleigh number equation, which is Grashof number into Prandtl number gives us Rayleigh number, which is 3.725 into 10 to the power 8. So with this we complete our conduction, heat exchangers and convection based questions. So next video would be on radiation practice question. Thank you.